Imagine, for just a second, stepping out of a spacecraft and landing on this shallow ocean planet.
Right, where the water is like barely knee deep.
Yeah, exactly. And the gravity feels maybe a little heavy, pulling at your boots. But otherwise, I mean, it just feels like you're standing on a slightly strange beach.
But there is a catch.
There's a massive catch, and it is completely mind-bending. Every single hour that passes for you while you're walking around on this planet equals 7 years passing back home.
Wow. Yeah, it's such a heavy concept.
Right. Like you spend a casual afternoon collecting a few water samples, and an entire lifetime has gone by on Earth. Your friends, your family, your kids, they've all aged decades.
You haven't even, had time to get hungry for dinner yet, and everyone you know is an old person.
It is a terrifying scenario.
It really is, and a fascinating one. It's famously the core dilemma brought to life in the movie Interstellar.
Yes, exactly.
But what makes it so gripping isn't just the drama of it. It completely shatters our default assumption about reality.
Because we walk around all day assuming time is just this universal, absolute thing, right? Like a metronome ticking away in the background of the universe.
Right, keeping the exact same beat for everyone. But that assumption is completely wrong.
And that is our mission for this deep dive. We are going to unpack the actual hard science of time dilation. Specifically, what happens when you get up close and personal with a black hole.
Because it's not just movie magic, is it?
Not at all. I've been digging through a massive stack of sources for this. We're talking dense university physics textbooks, articles from the Magna Scientia Journal, and technical publications from NIST.
That is quite the reading list.
Oh, I also fell down some incredibly intense physics forum rabbit holes and Reddit threads where people were ruthlessly debating the actual math behind Interstellar.
I love those forums. People get so passionate. But the overarching theme across all that data, whether it's a textbook or a forum debate, is that time is far more flexible than we think.
Far more localized, yeah.
Exactly. More localized than our everyday human experience allows us to actually feel.
Okay, let's unpack this. Because to truly grasp how time can basically come to a screeching halt at the edge of a black hole, we actually need to look a little closer to home.
Right. We can't start at infinity.
Exactly. Before we jump into the extreme sci-fi stuff, we have to prove that time is an absolute right here in our own solar system.
Because this isn't just theoretical. Time dilation is happening to you listening to this right now down here on Earth.
So to understand the mechanism behind it, we kind of have to rethink the classical Newtonian view of the universe, right?
Yeah, we really do. For centuries, physics treated space and time as completely separate entities.
Like space was the physical stage, and time was just the clock on the wall.
Precisely. A clock that ticked at the exact same rate for every single person in the audience, no matter where they were sitting or how fast they were running around the theater.
But Einstein changed all that.
He did. His theories of relativity proposed a radically different underlying mechanism. Time and space are entirely interwoven into this dynamic, flexible, four-dimensional structure.
Which we call space-time.
Right, space-time.
I was struggling with why time has to be flexible, though, until I read the section on the speed of light in the textbook sources.
Yeah. The cosmic speed limit.
Right. The universe has a hard speed limit. The speed of light is constant. It never changes no matter how fast you are moving.
That is the pivotal concept. If the speed of light is an absolute, unchanging constant for every observer, well, something else has to give when you start moving at different speeds.
And the thing that bends to accommodate that constant speed of light is time itself.
Exactly. Time bends.
Which sounds like something we'd only have to worry about if we were flying around in rockets at light speed.
Yeah.
But we actually have to account for this weirdness in our everyday technology.
Oh, absolutely. The sources point to the Global Positioning System, your standard GPS, as the ultimate real-world laboratory for time dilation.
GPS proves that relativity is an inescapable engineering reality.
If we want our maps to work, we actually have to calculate for two competing relativistic effects.
Acting on the GPS satellites, right?
Right. The ones orbiting roughly 20,000 kilometers above our heads. It's a constant tug of war between speed and gravity.
Let's break down that tug of war. The first effect comes from special relativity, which deals with the speed aspect.
Okay, so how fast are they going?
These satellites are zipping around the Earth at about 14,000 kilometers per hour relative to the ground.
Moving at that velocity engages the first mechanism of time dilation. Einstein's math dictates that a moving clock, when observed from a stationary point, actually ticks slower.
So because the satellites are moving so fast relative to us on the surface, their onboard atomic clocks slow down.
Yeah, they lose about 7 microseconds a day compared to our clocks on the ground.
7 millionths of a second. I mean, it's an almost imperceptibly small amount, but I love this analogy I found in the physics forums to help visualize why it happens.
Oh, the shared budget analogy.
Yes. Think of your movement through space and your movement through time as a shared budget.
It's a remarkably elegant way to frame it.
If you are just standing completely still, doing nothing, you are spending your entire budget moving through time. You are aging at the maximum local rate.
But the second you start moving,
Exactly. The faster you speed up through space, the more of your budget you have to allocate to spatial movement.
which inherently leaves you with less budget to spend on moving through time.
So your time literally slows down relative to the person who is just standing still.
The mechanism holds up perfectly.
Yeah.
But, that is only half of the GPS equation. We also have to account for general relativity.
Right, which deals with gravity, the second part of the tug of war.
Because the satellites are 20,000 kilometers up in the air, they are sitting in a much weaker gravitational field than we are down here on the surface.
And the weaker the gravitational field, the faster time moves.
Exactly. So while their sheer speed is causing the satellite clocks to lose 7 microseconds a day, this weaker gravity is causing them to speed up.
How much do they speed up?
They gain about 45 microseconds a day.
Wow. So they lose 7 but gain 45. The gravitational effect definitely wins the battle.
It does. The net result is that the clocks on the satellites run fast by a very specific, calculable amount.
38 microseconds a day.
Yep. Every single GPS satellite is deliberately launched with a clock set to run slightly slow before it even leaves the ground.
Purely to counteract the exact phenomenon. That's wild. If engineers didn't build in that 38 microsecond correction, the GPS on your phone would drift by roughly 10 kilometers a single day.
You try to navigate to a coffee shop across town and end up in a different city entirely.
All because we didn't account for the fact that time moves differently up in space.
What's fascinating here is that scientists didn't just stumble into this with GPS. They actively proved the gravitational side of this shared budget with a brilliant experiment.
Oh, the 1976 one, Gravity Probe A.
That's the one.
I saw this in the notes. They launched a highly precise maser clock, which uses microwave oscillations to keep incredibly accurate time on a rocket that went 10,000 kilometers straight up into the air.
And by comparing the continuous telemetry of the clock in space to a duplicate clock on the ground, they directly measured gravitational time dilation in real time.
So what did the data show?
It definitively proved that at that high altitude, in weaker gravity, the clock ran 4.5 parts in 10 to the 10th power faster.
Which translates to gaining about 1 extra second every 73 years.
It's such a tiny sliver of time, I know, but it confirms the mechanism.
It totally does. But, this brings up a really fundamental hurdle I hit when reading the sources.
Oh, what's that?
If gravity is the thing that is warping time, what actually is gravity? Because we all have this image in our heads.
Let me guess. The classic science class visual.
Yeah. The heavy bowling ball sitting in the middle of a two-dimensional rubber sheet making a big dimple, and the marbles roll down into the dimple.
Ah, the infamous rubber sheet analogy. It is ubiquitous in classrooms, and as our physics forum sources aggressively point out, it needs to be completely discarded.
The forums were brutal about it. They really hated it. But why is it so bad? It seems intuitive enough.
Well, it relies on a logical fallacy. It uses our intuitive understanding of Earth's gravity, pulling the bowling ball down into the sheet to explain gravity itself.
Oh, right. Because in the vacuum of space, there is no down to pull anything into a dimple.
Exactly. Furthermore, space is not a flat two-dimensional trampoline bending into some mysterious fourth dimension.
So what should we use instead? We need a different mental model.
The forums actually suggested visualizing it as a three-dimensional block of squishy foam rubber instead of a flat sheet.
Okay, a 3D foam, I can picture that.
If you embed a massive object, like a star or a planet, into the center of a giant block of 3D foam, it doesn't pull the foam down.
Right, because there's no down.
Instead, it pulls the foam inward toward its center. It bunches the foam up. The closer you get to the massive object, the more dense and compressed the squishy space becomes.
Okay, I'm picturing this block of foam tightly packed around a star. And here's where my brain got stuck earlier. I initially thought, okay, if I shoot a bullet past this star, it hits the bunched up, dense foam. So it experiences friction, slows down on one side, and turns inward. but the sources were absolutely adamant that gravity has absolutely nothing to do with density, drag, or friction.
The friction idea is a very common trap when you use the phone analogy. The bunching up isn't about physical density. It's about the geometry of space itself changing.
Okay, so if not a bullet in foam, what is it?
Instead of a bullet, imagine driving a car where the wheels on the left side are suddenly forced to drive on a track that is physically shorter than the track the wheels on the right side are on.
Well, if the left wheels cover less distance than the right wheels, the car's going to naturally turn to the left, even if I'm holding the steering wheel completely straight.
That is the exact mechanism. In this scenario, the car is a photon of light,
And light is always trying to travel in a perfectly straight line, right?
what physicists call a geodesic. But when it passes near a massive object, the actual geometry of space it is traveling through is curved and distorted.
The tracks are uneven.
Exactly. The light is going straight, but the space it occupies is bending.
So gravity isn't a magical invisible tether pulling things like a magnet. It is simply objects following straight lines through curved geometry.
This was the monumental shift in physics, and Arthur Eddington proved it visually during a solar eclipse in 1919.
How do you prove it?
He observed that the light from distant stars appeared to shift position when it passed close to our sun. The sun's mass was curving the geometry of space around it.
Forcing the starlight to travel on a bent path to reach our telescopes.
Yes, and we can see this today on a mind-boggling scale with the James Webb and Hubble telescopes.
The university cosmology text we reviewed went super deep into this, gravitational lensing.
Right. Galaxy clusters like Abell 370 are so unspeakably massive that they warp the 3D geometry of space around them like giant magnifying glasses.
We can literally see the distorted, stretched images of galaxies sitting 25 billion light years behind them.
And we are seeing those distant galaxies purely because their light was forced to navigate the bent tracks of space around the foreground cluster.
Okay, so spacetime is this squishy 3D geometric web that dictates how light and time have to behave. Here's where it gets really interesting.
Oh, we're going to the extreme end now.
Yes, because I was reading the textbook sources about black holes, and the math for a standard one just completely broke my brain. Let's crank the mass up to infinity.
We aren't talking about a planet or a galaxy anymore.
No?
We enter the realm of a standard, non-rotating black hole, what physicists refer to as a Schwarzschild black hole.
And this is where the physics of time become truly terrifying.
Because the concept of a shared reality shatters completely. Everything depends entirely on who is doing the observing.
The event horizon is the boundary, right? The Schwarzschild radius?
Right, the ultimate point of no return where the gravitational curve is so steep not even light can escape.
If time stops at the edge, do you just freeze? Let's say I'm watching you fall toward this event horizon from a safe distance in my spaceship. What do I actually see?
Okay, so from your perspective, sitting safely far away, you are bound by what physicists call coordinate time.
Coordinate time. Got it.
As I fall closer and closer to the event horizon, the space-time geometry around me is so intensely curved that my time budget is being almost entirely consumed by gravity.
So you will appear to slow down.
Dramatically.
So you don't speed up as you fall, you just hit the brakes.
According to your coordinate time, yes. In fact, the math dictates that it will take an infinite amount of time for you to see me actually cross the event horizon.
Wait, an infinite amount?
Yes, I will appear to slow down endlessly until I freeze in place right at the absolute edge.
That is haunting. You just freeze there as a statue forever.
I do, but I don't stay visible. Because the light bouncing off my spaceship has to fight its way up out of that incredibly steep gravitational well to reach your eyes.
And that takes energy.
Massive amounts of energy. As a photon of light loses energy, its physical wavelength stretches out. This is the mechanism known as gravitational redshift.
Okay, so it's like watching a YouTube video on a terrible internet connection.
I like where you're going with this.
The video starts buffering, right? The frame rate drops and you go into super slow motion.
Right.
Then the resolution gets worse and worse, getting pixelated and distorted. That's the wavelength stretching, the redshift, until the video just completely freezes on a single blurry red frame forever.
The buffering video is a fantastic way to conceptualize coordinate time. My ship would shift into the red end of the visible spectrum, then stretch into infrared, then microwaves, until I completely faded from your view.
But remember, that is only my reality from the outside.
Exactly. My reality, falling into the black hole, is governed by what is called proper time.
Right, your local internal clock. So how does the YouTube video look from inside the video?
It doesn't buffer at all. As I fall toward the event horizon, I don't feel time slowing down in the slightest.
Really? You feel totally normal.
If I check my pulse, my biological clock, my heart beating, my lungs breathing, everything feels completely standard. Yeah. I don't freeze.
So what happens?
I cross the event horizon in a finite amount of time, experiencing a very quick one-way trip into the dark from which I can never, ever return.
It's a total dual reality. You just pop through the horizon in a few seconds on your watch, completely oblivious, while I sit outside in my ship and watch you slowly stretch into a red ghost over eternity.
It perfectly illustrates the core tenet of relativity. There is no single universal now. My now and your now become completely disconnected based on the geometry of the space we are occupying.
Which brings us perfectly back to where we started with the hook of this deep dive.
The astronauts in interstellar landing on Miller's planet.
Yes, which is sitting right on the edge of the supermassive black hole they call Gargantua. In the movie, the crew explicitly states the conversion factor. 1 hour on that planet equals 7 years back on Earth.
That is roughly 61,400 Earth seconds passing for every single second they spend on the planet.
I have to push back here, though, because when I read about the Schwarzschild black hole, it said the gravity at the horizon is infinitely steep.
Is it?
Wouldn't gravity that strong just crush the ship instantly? How is a planet even physically existing there without being shredded?
You are hitting on a major scientific hurdle that the filmmaker, Christopher Nolan, actually had to solve.
Did he just ignore it?
No, he worked closely with Kip Thorne, a Nobel-winning theoretical physicist, to design the actual math of the movie. And you are correct. If Gargantua was a standard, non-rotating Schwarzschild black hole, the astronauts would be dead long before they experienced that level of time dilation.
Right, the tidal forces would get them.
The difference in gravitational pull between their heads and their toes would be so extreme they would be ripped apart, a process literally called spaghettification.
Spaghettification. Such a funny word for such a grim concept.
And a planet couldn't maintain a stable orbit that close to a non-rotating black hole anyway. It would just spiral in.
So how did Kip Thorne make the 1 hour to 7 years ratio scientifically viable?
He calculated that Gargantua couldn't be standard. It had to be a Kerr black hole.
A Kerr black hole, what's the difference?
A Kerr black hole is supermassive. But crucially, it is spinning.
Spinning, like fast.
Spinning at nearly the maximum possible speed allowed by the laws of physics.
How does the spin fix the problem of the planet being shredded?
When a mass that large spins that fast, it literally drags the geometric fabric of space-time around with it.
Like a spoon furiously stirring a thick bowl of syrup.
Exactly. This mechanism is called frame dragging, and it creates a swirling region outside the event horizon known as the ergosphere.
So the space itself is spinning around the hole like a whirlpool.
Exactly the right visualization. This frame dragging effect essentially pushes the safe orbital distance further out.
Oh, I see.
It allows a planet to orbit at close to the speed of light, stabilized by the swirling space-time. This minimizes those crushing tidal forces.
It allows the planet to sit deep enough in the gravitational well to experience that insane time dilation without being immediately destroyed. That is just brilliant. They literally reverse engineered a specific mathematically sound type of spinning black hole just to make the plot point of the movie physical possible.
It's amazing what physics can accommodate if you do the math right.
And there's this amazing detail I found in a YouTube analysis about the film's musical score.
Oh, I haven't heard about this.
During the entire tense sequence on Miller's planet, composer Hans Zimmer put a very faint rhythmic ticking sound in the background music.
Okay.
If you run the math on Kip Thorne's time dilation ratio, every single tick in that song represents about 21 hours or roughly 77,000 seconds passing back on Earth.
Wow. It grounds the abstract, terrifying math into a visceral auditory experience. Every tick is a day gone.
It's so intense.
It is. But if we connect this to the bigger picture of our sources, we also have to acknowledge where the movie consciously chose to ignore physics so the audience wouldn't be completely overwhelmed.
Yeah, they had to dial back the realism somewhere. What did they leave out?
Well, we talked earlier about gravitational redshift, how light loses energy and stretches out when fighting its way up out of a deep gravity well.
Right, the buffering YouTube video.
The reverse mechanism is also true. Light falling down into a gravity well gets heavily compressed, gaining energy, which is called blue shift.
So all the ambient starlight from the rest of the universe falling down onto Miller's planet
would be massively warped. Because the time dilation is so extreme, the visual spectrum of light entering the vicinity of that black hole would be entirely shifted.
It wouldn't look normal.
The sky wouldn't look like a standard sky at all. The starlight would be compressed into blinding, highly energetic blue-shifted radiation. The visual reality would be heavily distorted.
Did they know about this when making the movie?
Kip Thorne actually calculated what this would look like.
Yeah.
But Christopher Nolan decided that depicting it accurately would be far too confusing visually for a mainstream moviegoer.
So they allowed the light to behave relatively normally on screen. I guess you can only bend the audience's mind so much before you break the narrative. Oh, and I assume the magical time-traveling gravity bookshelf at the end of the movie isn't standard black hole physics either.
The Reddit community heavily debated that ending, but it is explicitly a science fiction construct. The Tesseract was a 4D structure placed inside the singularity by advanced beings.
So it's not a natural phenomenon.
No, we still don't actually know what happens at the very center of a black hole.
So what does this all mean? We started with the atomic clocks on GPS satellites and ended up writing the frame-dragging ergosphere of a spinning Kerr black hole.
It's been quite a journey.
I think the takeaway for you, listening right now, is that you have to abandon the idea of a universal ticking clock. Time is a localized, flexible dimension.
It really is.
It is an active geometry stitched right into the space you occupy, whether it is throwing off your phone's navigation by 38 microseconds a day or costing you 7 years of Earth time for a 1-hour stroll on a tidal wave planet.
Your reality, your time, depends entirely on where you are and how fast you're moving.
It fundamentally changes how you view your place in the universe.
It does. And this raises an important question, one that brings us to the absolute bleeding edge of modern physics.
Ooh, what's that?
We have spent this entire deep dive discussing how general relativity beautifully and accurately describes time dilation outside the event horizon.
Right.
But the truth found in the Magna Scientia source is that the mathematics of classical gravity entirely break down at the horizon itself.
Break down. You mean Einstein's math just stops working?
It produces infinite nonsensical results. To understand what happens inside a black hole, we actually have to introduce quantum mechanics.
The physics of the incredibly small.
Exactly.
Yeah.
But when we mix quantum mechanics into the incredibly heavy, dense environment of a black hole, our theories violently collide.
So the two rulebooks of the universe refuse to talk to each other.
They completely contradict each other, which leads to the information paradox.
What's the information paradox?
But if you fall in, does the event horizon actually destroy the quantum information that makes up the atoms of you?
I mean, if it's a one-way trip, you'd think so.
But that violates the core rules of quantum mechanics. Information cannot be destroyed.
Wow.
Furthermore, does time even exist as a smooth geometric curve inside a black hole? Or does space-time itself shatter, becoming quantized and broken into little discrete chunks?
So we don't even know if time survives the trip past the event horizon.
We don't. It leaves us to ponder a truly unsettling possibility. That time, as we intimately know and experience it, simply ceases to exist entirely at the bottom of the ultimate gravitational well.
A place where time simply stops existing. That is a heavy thought to carry with you today.
It really is.
Just remember, the next time you look at the clock on your wall or the phone in your hand, it's not telling you the time of the universe.
Nope.
It's only telling you the time right here, right now, in your specific little dent in the geometry of space.